I'm going to describe the mathematical theory of fatigue damage, and in particular the damage that you can associate with random signals. Let's consider a random variable that I will call d with a tilde to denote the fact that it's a random variable, and I'm going to write the following formula. Summation over j. Here I have a random variable n tilde j, and I will divide by capital Nj. Capital Nj is not a random variable, and let me define these variables. In particular, d represents, as I said, damage, and it's a random variable. Whereas lowercase nj represents the number of cycles that occurred at the level j. So let me explain it a little bit more in detail. The level j is characterized by some kind of stress level, sigma j. So this is a stress which according to our model is proportional to displacements that I will call Zj. So Zj is the relative displacement, and I will describe it a little bit more a few minutes later. And K is a constant. It is just a constant of linear proportionality between stresses and displacements. And we have to you have to think of the fact that sigma j is the stress level that's going to be applied on some kind of material nj times, and capital Nj on the other end is the number of cycles that would lead the material to failure at level J. So this is some kind of characteristic of the material. And how do you count the number of stresses? Well, this is not going to be explained in this video, but let me mention just one method that allows you to count the number of cycles starting from a signal over time, and this signal, for example, can be a stress. So it's a stress signal, so it's some kind of function sigma of t. It is a function which depends on time, and based upon the shape of this function and the number of peaks, you can count the number of stress levels, sigma j's. And one very famous method is, for example, the rainflow counting method, which is very useful also numerically. And I'm not going to get into the details, at least in this video. I'm not going to explain how to count the number of stresses for very complicated signals. Now, to explain what Zj is, well, I said that this is a relative displacement, and in particular, if you want to understand it better, we consider a single degree of freedom system, SDOF, SDOF system, it's also called SDOF system, where we have an input signal, and then we have an output signal, which will depend also on the transfer function of this single degree of freedom system. Let's call the input signal, which could be, for example, also a vibration. But let's think of this as a displacement. So it's not an acceleration, but it is a displacement. So it has units of length. And then here we have the output, which is the signal x of t. And then if we take the difference between x of t and y of t, this is what is called the relative displacement z of t. And this is actually what's in here. This is the jth relative displacement related to the stress level j. So when we talk about z, we are really talking about this kind of system. And we will see that the damage will be relatable to z of t. So based upon the relative displacement caused to the system, we can find a mathematical way to express the damage. Now we need another equation, and the equation is related to high cycle fatigue, meaning that we are considering only a very high number of cycles caused to the material. Because for high cycles, which is actually one of the most frequent causes of failure for materials, well, there is also low cycle fatigue, and we should also explain what fatigue is in general, but we are just trying to convey the basic idea behind this. So, in general, when we have some kind of stress. And let's think of this signal, sigma of t. It is a stress signal, a stress caused upon a material. And let's say that the material can endure the following level of stress. So this level here is the maximum that material can resist. So if we go beyond this level, the material is going to break. And if we stay below, the material will not break. But even if sigma of t is much lower than this value, which could also be reported here in the negative values. So if we do not go beyond this line or this line here, so if the signal does not grow beyond this line, you might say, well, it's never going to break. But that's not the case. That might not be the case. Because all these stresses are going to be cumulative. They might increase the damage. And therefore, when this summation here increases too much, then we might have failure. And in principle, this occurs when this is equal to 1. But this is a simplified theory, so this would not occur in practice in most applications. But in general, if you think about the stress level sigma, and then we have lowercase n tilde, which is the number of times which this stress level has been applied to the material, and then we have capital N, which is the maximum number of cycles that the material could tolerate before going to failure, then the damage will be n tilde over n, if this is the only stress level applied to the material. And if this is equal to 1, then we get a failure, which means that, of course, lowercase n is equal to capital N. So this is when we get a failure of the material. A failure due to fatigue. And we are going to consider only high cycle fatigue, which is basically, let's say, something related to a high number of cycles. And this high, let me try to state it more precisely, it's of the order of 10 to the third or greater than this. So greater than 10 to the third, and in particular, we are talking about usually between 10 to the third and 10 to the eighth, for example. So we have a very, very large interval where high cycle fatigue comes into play. Another equation that we should consider for high cycle fatigue is the following. This is the relation for high cycle fatigue. Capital Nj times sigma j to the power b is equal to a constant c, which means essentially that if we draw this curve in the sigma j and j plane, and remember that this should hold only for very high cycles and for a very high number of cycles, and the number of cycles you can see from here. This is the maximum number of cycles that the material can tolerate. So we should start somewhere here where Nj is large enough, because here we have a low cycle fatigue and we're not going to consider that. And the curve behaves more or less like this. It is this kind of behavior. The greater the number of cycles Nj, usually the lower the stress level that can be endured by the material. So you can think about it this way. So the larger this number, of course, the lower this one would be, right? Because the material will endure a greater stress level for a number of cycles that is small enough. That's the kind of thinking process that you should go through, because you should always speak about cycles and stresses in pairs. So you should always think of the stress level, but at the same time the number of cycles with that kind of stress level. And this is a simplified theory where we assume for simplicity that there are no uncertainties in the material. So this constant here and this constant here, this b, they are related to the material. And we assume simply that there is no randomness in the material, which is a simplified version of the model. You can overcomplicate things, and it depends on applications. But even if the simplifications are quite brutal, this simplified theory can give you very interesting ideas behind this kind of theory on stochastic signals and fatigue damage and how their relationship occurs. Now, let's get back to the expression that we wrote up above. We have the damage equal to the summation over J of N tilde J over capital Nj. Now we can also use this relationship. And of course, this is equal to summation over J N tilde J sigma J to the power B divided by C. And we can also use the following relationship here. So we can simply call relative displacements into play. So we can rewrite this as k to the power b over c summation over j. And then we have n tilde j zj to the power b. Now, we can also think of each load cycle as occurring an infinitesimal number of times. So we can think of these stress levels to be distributed continuously. And basically, it means that in this case, the damage could be represented with an integral. So we have to integrate over dn, and then we divide by capital N. And these are continuous variables. So in this case, we are going to get something very similar. And so we can rewrite this as integral sigma to the b over c dn tilde. And we have to find a way to express dn tilde. So dn tilde, which is the infinitesimal number of cycles, and this infinitesimal number of cycles can be thought of in this way. So let's draw these two horizontal lines where this represents the stress level sigma, and this will be sigma plus a small increment d sigma. And here we have some kind of signal that might be complicated, and what we are really interested in is to find the number of cycles that occurred in this small interval here, so inside this region. And in particular, we can find that if we consider the distribution of the peaks of the signal. So we need to find the distribution of the envelope of the signal, which is something that is related to the Rayleigh distribution for Gaussian signals. We'll get back to that in a future video. And this distribution will depend, we can think of this as a function of the stress level, or if you want, Z. So we assume that there is a linear proportionality between sigma and Z. So it's really the same if you write sigma or Z for the distribution, right? Because Fp of sigma d sigma will be equal to Fp of Z dz, where we can easily check that this is the case. There is a linear proportionality, so it's not important if we use the function f of sigma or f of z. So this will tell us what is the probability to find the peaks between sigma and sigma plus d sigma. But this is a probability. If we want to find the number of cycles between sigma and sigma plus d sigma, then we have to multiply this probability by the total number of peaks, of positive peaks in the signal. So we are going to consider only positive peaks because we are assuming that this sigma here is a non-negative. It's a non-negative quantity according to the theory. So we are also going to neglect possible stress levels that are negative, and we're not going to consider them, but it actually makes sense for most signals that occur in real life, in real applications. And so the total number of peaks, of positive peaks that I have in the signal, I will write it like this. So I will have a random variable n tilde p plus, so this indicates the number of positive peaks per unit time. So we need to multiply this by the total duration of the signal in order to get what we seek. So making this substitution, we'll get np plus times t divided by c, and then we have an integral from 0 to infinity, so we'll have to integrate from 0 to infinity sigma to the power b fp of sigma d sigma, where f of p is the distribution of the peaks. We found that, for example, for Gaussian signals, this will be the Rayleigh distribution. And if we want to find a scalar for the damage, because remember that this is not a scalar, this is a random variable, then if we want to find a scalar, we have to take the expected value of the damage that we are going to define simply as d without the tilde. So this will be equal to the expected value of np plus, so the number of positive peaks per unit time, and we will have to find it according to some theory. Then we multiply it by t, divide by c, and we integrate from 0 to infinity. And if you want, you can also use the relation between sigma and z. So you can rewrite this as k to the power b, if you want, and then here we have z to the power b fp of z dz. You can write it like this, or you can use a sigma. So if you use sigma here, you don't have k to the power b. Here you have sigma to the power b, and here you have fp of sigma d sigma. So for now, let's write it like this, right? This is the formula, and next time I'm going to find a way to express mathematically this scalar here, the expected value of the positive number of peaks per unit time.